I think we got into last time during lab. Chapter 12 is about bonding. So we're going to look at, we talked about different types of bonding. We talked about ionic bonding, where we have metal and a non-metal, and a transfer of electrons from the metal to the non-metal, resulting in cation and anion formation. We showed how to draw those using Lewis dot symbols. With those, we do include the charges when we draw them. Obviously, the electrons being transferred as well. We talked about two types of covalent bonding. Basically, that is sharing of electrons. That is between two nonmetals. And the difference there is, again, they'll just kind of agree to share electrons. The sharing could be unequal, which results in a partially positive charge and a partially negative charge on the bond. And that's what's referred to as a polar covalent bond, or just a polar bond. We also could have sharing, which is considered equal sharing. And that means that the electrons will be shared equally between the two atoms. And it's really sort of the difference in electronegativity that helps us determine sort of how the sharing of those electrons are going to be. And in the case of equal sharing, that's what's considered a nonpolar bond. So we can use the electronegativity values if we have them available to us to take the difference. And remember, anywhere from basically 0 to 0.4 is considered nonpolar when we have the difference in electronegativity. Anything above that, 0.5 to less than 2 is considered a polar bond. And anything above 2 is considered ionic. A reminder that really you don't even need the electronegativity values to do an ionic bond, because it should be a metal and a non-metal. Always when those come together, those are always going to be a ionic bond. Also remember that you don't really need the values if you're comparing two elements that are in the same row or the same group on the periodic table. Most likely, if they're in the same row or group on the periodic table, there is going to be a good enough difference in electronegativity that you're going to have a polar bond that could happen. But we should also remember that there is that diagonal relationship that we talked about, like nitrogen and chlorine, or carbon and sulfur. When you look kind of diagonal of each other on the periodic table, they will sort of have the same electronegativity values and can give you a nonpolar bond. I believe we ended up talking about actually drawing Lewis structures for covalent bonding. And really, there's several steps that you kind of want to follow when you draw Lewis structures. You want to basically count up the valence electrons. You want to have the logical arrangement of the atoms. Remember, that is typically the least electronegative atom in the center. You then want to make one single bond from the center atom to all the outside atoms. You want to figure out how many electrons you have left to distribute. Then those leftover electrons go on as pairs of electrons, so dots basically, on all the outside atoms. If you should fill up all the outside atoms with 8, then you go to the central atom. If you still have electrons to go, then you go to the center. So outside first, then center. Really, at that point, if you got to the center atom, you should have basically used up all your electrons. You want to make sure everybody has met the octet rule. If not, then at that point, that is typically where we want to kind of do double bond or triple bond to sort of fix it. So remember, you don't want to kind of double bond or triple bond out of the gate. Kind of want to save those for fixing it. I think we finished up on one where we did double bond. I think we did the NO3 minus, if I'm not mistaken, was the last one we did. Any questions on any of that stuff there we talked about last time? All right, so let's draw a few more here and kind of see. All right, so take a few minutes here and whoops, come back maybe. Why don't you draw the Lewis structures for these guys? See how you do. Take a look, see how you're doing. So remember, we'll start with SO2 here. So really one of the first things you want to do is calculate up the total number of valence electrons. Remember that the valence electrons equals the group number. So sulfur is group 6, so that would be 6. There are 2 oxygens, which are also group 6, so that is going to be 12 and 6 will be 18 valence electrons here. When we look at sulfur and oxygen on the periodic table, sulfur is lower than oxygen, which means it's less electronegative because they're in the same group. That means the sulfur should be in the middle with some oxygens on the sides there, perhaps. And we're going to do a single bond to each of them. That's going to give us 2 that we've used. We have 14 more to go. That's going to go on the outside first. So that's going to be 2, 4, 6. Remember, we want to put them on as pairs. So all the outside ones have 8, except for hydrogen that should only have 2. So that is 2, 4, 6, 8, 10, and 12. At this point, I put 16 electrons. I filled up all the outside ones. I still have electrons to go. They then should go to the center as dots. And that is how dots get to the center. And they should have dots, by the way. At this point, that is 18 electrons. In this case, everybody is good except for the sulfur in the middle. The sulfur in the middle only has 6 electrons. This is a case where we can make a double, or which oxygen we make the double bond, but as we talked about last time, we don't draw the line, the electron from an outside one, and we're bringing them in to make double bond. And at this point, you side like that. And for structure for, and there, these are 2. These are what are known as resonance structures. All the resonance structures, unless you're asked to do so, but either one of those pictures would have been sufficient. Any questions on any of those steps there? Yes, sir.
It is also Valence electronic to ozone.
Good to know. It does. It has the exact same. It does as well. Yep. Just put an O in the middle. Yes. It really doesn't, as long as you take a pair. So personally, I usually on double bonds, a lot of times people will put the kind of dots like they're kind of on the outside, I call it, I guess. But it really doesn't matter as long as you take the pair. So, you know, if you did your double bond and you left the electrons like that, it's okay as well. Yeah. Other questions? All right, so moving on to SH2 here. SH2, once again, 6 for the sulfur, 2 times 1 for the oxygen, gives us 8 valence electrons. As we talked about, obviously hydrogen should never be in the middle. So it's going to be sulfur once again here in the middle. We're going to do hydrogens on the outside. We're going to do a single bond to each of the outside atoms. That's going to give us 2 and 4 electrons, leaving us 4 to go. Once again, hydrogen is done on the outside, no dots ever. So we are going to bring those 4 electrons to the center here, again, as pairs of electrons. At this point, we should now have 8 electrons. The sulfur in the middle has 8, which makes it happy. And the hydrogens have 2, which is all hydrogen should ever have. Yeah. Any questions on that one there? Coming to our NH4 plus, once again, nitrogen is 5 plus 4 for our hydrogens, and they're each 1. We do have a plus here, which means it has lost electrons, so we need to subtract 1. Otherwise, we get the wrong count. And in this case, this will also give us 8 valence electrons. In this case, we will again do nitrogen in the center, hydrogens around here. We're going to do a single bond to each of the hydrogens. And frankly, that's 8 electrons. So we are done at that point. Nitrogen in the middle has 8. Each of the hydrogens have 2. We do usually put a little bracket around it, and the charge to indicate that it is an ion in this case. Any questions on that one there? Looking at CO2, that's going to be 4 for the carbon, 2 times 6 for the hydrogen. That's a lot of math there. That's 16 we'll go with. We're going to put carbon in the middle. Once again, if you look, carbon is to the left of oxygen. They're in the same row, which means carbon is less electronegative. So carbon will go in the center. We'll go oxygens on the outside there. A single bond to each of them. That's going to be 2 4 electrons, leaving us 12 more to go. So that will be 2, 4, 6, 8, 10, 12. At that point, we have 16 electrons, and our carbon in the center is short. It actually only has 4 electrons. So at this point, we want to try to fix it by making a double bond like we did previously. So we'll take a pair of electrons, we will bring it in. When we do that, we will end up with a double bond on the right, a single bond on the left. Did this double bond fix carbon? Did not. Got it closer, it got it to 6. So in this case, we would want to actually make another double bond here. You kind of want to exhaust all your double bond options before you triple bond. So in this case, we will take a pair of electrons again from the other side and bring it in on that side. That will then get us a double bonded oxygen on each side. And at this point here, we now have 2, 4, 6, 8 electrons on everybody. We still have just 16 electrons. Any questions on that one there? So again, in this case, we needed 2 double bonds there to get everybody 8. Lastly, here we got a little N2 action happening. So we'll do N2, which would be just 2 times 5 is 10 electrons. In this case, there really is no center atom, so you could just kind of put them side by side if you like. We could do the same steps. We're going to make a single bond. We then have 8 more electrons, so we're going to put them on the outside one first, RA outside one first. So 2, 4, 6, 6, and 8. At this point here, the nitrogen on the right is good, but the nitrogen on the left is not good. So we're going to try to fix it by making a double bond. So we'll take a pair of electrons in to do so. That is going to get us a double bond. And we can see we got closer for the guy on the left. We got it to 6, but it is still short in this case. So at this point, there's nowhere else to make a double bond. So now we would go to a triple bond. And once again, it works the same way. We once again are going to take a pair of electrons in to make that triple bond. And when we do, we end up with a triple bond like so. At this point, both nitrogens now have 8 electrons around them. And that is how it gets to a triple bond. Yeah. Any questions on drawing Lewis structures? So if you follow these sort of steps, it should really lead you to a pretty good structure. Again, if you kind of do piecework and try to put things together, a lot of times you end up with a not a great structure, too many electrons, not the right number of bonds, and stuff like that. Any questions on Lewis structures? Obviously, what we've been talking about here, going through those steps, is what we do when we're drawing electrons. Are pretty much what we use these steps for. All right. So here is CO3 2 minus, which is very similar to NO3 minus. Again, we would fill up our octet, see that carbon is short. So once again, here we can make a double bond to fix it. All right, so we talked a little bit about resin structures, but we'll get back to that in just a sec. But first off, let's talk a little bit about bond length. So bond length is the distance between the 2 nuclei in the bonded atom where they're sharing electrons. And you don't have to memorize any of these numbers. But when we look at, say, a single bond between carbon-carbon, double bond, and a triple bond, what we see is a single bond is 154, double is 133, and a triple bond is 120. When we look at, say, the carbon single bond, carbon nitrogen single bond, carbon nitrogen double and triple bond, It goes from 143 to 138 and to 116. What we're actually seeing with these numbers is a single bond is actually the longer bond. When you bring those electrons in to make the double bond, everybody kind of moves closer together. And when you bring some more electrons in to make a triple bond, they get even closer together. So every time you sort of add on a bond, kind of bringing those electrons in between everybody is bringing the distance between the two atoms closer to one another, and the bond length gets smaller. That does relate to strength. So a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. And I kind of think about it like a brand new pencil out of the box. You know, it's nice and long. You could take it and snap it pretty easily. You take like a chemistry test and you're left with like an eraser and like a nubbin of a pencil like that big, right? It's very, very hard to sort of break that in half. So the strength does increase with the number of bonds that you have. It's not like a double bond is twice as strong as a single bond or anything like that, but that's the general trend that you see. Triple bond is strongest, followed by double, and the single bond being the weakest of them all. Now, resin structures, as we've just been talking about, are structures that really do arise when there is, for lack of a better description, a couple of options or multiple options where you can make like a double bond, for example, like we saw in carbonate, like we saw in SO2. Again, resin structures are usually separated by this arrow here to indicate that they are resin structures. And the real reason is really these sort of double bond electrons. They're sort of what are referred to sometimes as being delocalized, which means they're kind of moving around. So at any given point, they may be on the oxygen on the left, maybe on the oxygen on the right in this case. So the real Lewis structure is probably somewhere in between the two. So because there's that option of those electrons kind of moving around a little bit, you could draw multiple Lewis structures. And again, the real option or structure is probably somewhere between them. As I mentioned before, if you're not asked to sort of draw all the resin structures, you don't need to. But if you are, then you should. Basically, the simple explanation is anywhere you could make the equivalent double bond, you could draw another structure. So like in SO2, we could double bond on the left, could double bond it on the right, and their equivalent sort of structures. So here is ozone, which was asked about earlier. Again, it is identical to SO2, as you can see. And you can also draw some resonance structures for it. Obviously, double bond on the left there, or double bond on the right. Here is a carbonate that we just saw. You don't have to worry about the charges that are there. But again, basically in something like carbonate, those double bond electrons are kind of moving around from one oxygen to the next, and it gives you some of these equivalent sort of structures. Benzene, we don't come across too much, but benzene is an organic compound. It looks something like this. And it's got 3 double bonds. And each of those spots are carbons, basically, with hydrogens attached. And you'll sometimes even see benzene written or drawn like that with a little circle to indicate that those double bond electrons are sort of moving around. If you ever take organic, you'll draw that all day. You'll be a professional. All right, so we'll skip through this guy here. So let's talk a little bit about some exceptions to the octet rule. Although in this particular class here, we are not going to really draw any exceptions to the octet rule. When you go to 1A, you'll do nothing but draw exceptions to the octet rule. But here we'll basically stay with the octet rule. The first exception to the octet rule is one that's known as an incomplete octet. And an incomplete octet is much like the name implies. There are certain elements that are perfectly fine with less than 8 electrons around them. And for example, boron is the most common one that you come across. It's sometimes referred to as being electron deficient. It is perfectly fine with 2, 4, 6 electrons around it, like we see there in boron trifluoride. And it's perfectly fine. It doesn't need a double bond out or anything like that to kind of fix it. It is perfectly happy in that situation. So for us, like I said, you're not going to draw any sort of exceptions, but you do need to know the exceptions. So the first exception is, for the most part, boron, aluminum, beryllium are sometimes included in those, but most of the time in covalent bonding, it's boron that we see that could have less than 8 electrons around it. Typically, boron will do the 6 there. A couple of other exceptions to the octet rule are an odd electron molecule. So these are guys where we end up with an unpaired electron, so like an odd number of electrons when you do your electron count there. And they're sometimes very, very reactive because they have that unpaired electron. So a lot of chlorine chemistry up in the atmosphere, chemistry, a lot of free radicals which have 1 electron. It's very, very reactive stuff. So an odd number of electrons is the second exception. And really the third exception, which is the one that you'll come across a lot in 1A, is the expanded octet. And the expanded octet are guys that have the ability to go to more than 8 valence electrons around it. And it usually happens on the periodic table right around sulfur, to the right, to the left, and down. And that is because when we look at the periodic table where sulfur is, that is the third period, which means that is n equals 3. And n equals 3, we have what type of orbitals there on the third energy level? We have s orbitals, right? We have p orbitals, like we do electron configuration. And on the third energy level, that is where we first start to see d orbitals. So they have d orbitals available to them. So these guys is where we start to really see those d orbitals available. And because they have those d orbitals available to them, they frankly have a place to stash some of the extra electrons. That means when we look at something like carbon, nitrogen, and oxygen, which is period number 2 on the periodic table, n equals 2, they only have s and p orbitals, which means those guys should never ever go above 8. They do have to obey the octet rule because frankly they don't have the d orbitals to stash the extra electrons. But it is common that you can't go sulfur left, right, and down where the nonmetals are and have sort of an expanded octet like SF6, for example. You basically have, I won't draw all the dots around the fluorine, but all the fluorines have dots, but you got 2, 4, 6, 8, 10, and 12 electron pairs around the sulfur there. Is also why when you Google something like sulfate, which if you follow our steps will lead you to this structure. But if you Google it, you might see a double bonded structure happening with sulfate. And that is because the sulfate here, or the sulfur, can do that. It can double bond. So for us, you shouldn't draw the one on the right because you should be obeying the octet rule, which would be the one on the left. Even though stuff that we won't talk about in this class, the guy on the right is actually the better structure of the two. But we will draw it like on the left there. So those are the 3 exceptions to the octet rule. Incomplete octet, less than 8, odd number of electrons, obviously an unpaired electron making it really reactive, and an expanded octet, sulfur left, right, and down on the periodic table have that ability to go over it. Once again, we will obey the octet rule for the most part in this class. Any questions on that there? We're talking about geometry here. We're talking about molecular geometry and sort of predicting it based on the central atom. So when we do geometry, it's really about the orientation of the electrons in 3-dimensional space and also the overall shape of the molecule. So we'll get 2 types of names. One is the electron pair geometry name is sometimes referred to. And that basically describes the orientation of the electrons around the central atom and we'll have the molecular geometry, which is also sometimes referred to as the shape. So we're going to talk about two types of names that go with the geometry for each of these. Again, one describes how the electrons are arranged, and one describes the overall shape of the molecule. It is based on the idea of electrons, and electrons obviously are negatively charged, which means when they do get around each other, they actually do want to try to escape each other or get away as far as possible. But because they are in a bond, they can't really do that. So they're sort of trapped in a sense. So the geometry that we go about is the valence shell electron pair repulsion model, our VSEPR, and it accounts for the geometry around the central atom. So when you do geometry for a molecule, it's all about the central atom. And a lot of what we draw in this class, you'll just have one central atom, but you could have multiple central atoms, but it's always a central atom that you want to do geometry for, from. It's basically divided into two types of categories. One where there are no lone pairs on the central atom, so basically no dots when you draw your Lewis structure, and one that does have lone pairs on the central atom, which basically means when you draw your Lewis structure, you will see dots. The most important thing when you're doing geometry is you treat double bonds or triple bonds as one electron pair and one bond. So they're effectively working as one unit. So counts as one electron pair and one bond. So that's the kind of important thing to remember. The other thing is, if you draw a resin structure, you can apply geometry to either of the resin structures. And usually if you drew them correctly, they'll end up obviously with the same geometry regardless. But that's the really main thing here. Central atom always, and single bond, double bond, triple bond, doesn't matter. All counts as one electron pair and one bond. So let's take a look at really the simplest molecules you could have. And that basically is diatomic. So you could have something like H2, F2, O2, N2, like we drew before, HF, HCl. Any diatomic molecule, regardless of if it is the same two elements, if it is different elements, if it is double bonded, single bonded, triple bonded, it doesn't matter. It's basically 2 points. What's that old saying? 2 points to connect them is a straight line. Yeah. So that's basically the geometry for anything that's diatomic. It is basically linear. So you don't have to think about it. Like I said, doesn't matter if it's single, double, or triple bond. It is basically going to be linear. A straight line between the two is always going to be the geometry of it. So those are like super simple. There is no central atom in that case, obviously, between two atoms. That makes it really, really simple. When we get into three or more atoms, we do have to look at a couple of things. First off, we do need to look at the central atom. So in this case, we are going to look at the central atom 100% of the time. In this case, we're going to do the number of electron pairs. Number of electron pairs here around the central atom is 2. They're both bonds. Yeah, so there's 2 electron pairs. The number of bonds here is 2 as well. Now, something with 2 electron pairs, the electron pair geometry. So I'll just call it the electron geometry, is also going to be linear. In this particular case, both of the electron pairs are bonds, which means those chlorine electrons basically are going to try to get away as far apart from each other as possible. Basically, as far apart as possible is opposite sides of each other. And that gives you a molecular geometry, our shape of linear as well, with a bond angle of 180 degrees. So what happens is those two electron pairs decide I don't want to be near each other. There's only two things bonded. They're able to basically go on opposite sides of the central atom and get as far apart as possible. So in this case, the electron pair geometry is linear. The molecular geometry is also linear, and the bond angle 180 degrees. The best way to do geometry is memorization. Most people can't visualize it in three-dimensional space, myself included. The best way to do it is with a little table. I want to make a bigger table maybe as we go through. Number of electron pairs, number of bonds, electron geometry, and molecular geometry. It's really the best way to kind of do it. Let's take a look at the next example. Would be a central atom where we actually do have 3 electron pairs. So once again, looking at the central atom, number of electron pairs is trigonal planar. I'm sorry, that is the name, but let's start with 3. Number of electron pairs is 3. Number of bonds in this case is also 3. So the electron geometry for something that has 3 electron pairs is trigonal planar. This is also sometimes referred to as triangular. Now, once again, what happens in this case is we have an extra bond in there. So instead of just 2 guys going on opposite ends of each other, they also have to keep a distance from the third guy. So basically these guys come down, this guy kind of goes up, away from each other. And our molecular geometry name is also trigonal planar. Mg for molecular geometry. It has a bond angle of 120 degrees because frankly, it makes a triangle. It makes a nice little equilateral triangle, which is why I sometimes refer to as triangular. Yes. We're going to actually talk about an example on that, and it does affect the overall geometry of it. So it does. We'll actually get to one just like that in just a second. Other questions? So in this case, both names are trigonal planar, describing the electrons and the molecular geometry. The next example would be a central atom where we have 4 electron pairs and also 4 bonds. So we got 4 electron pairs. Number of bonds is 4. Something with 4 electron pairs. The electron geometry name is tetrahedral. And once again, in this case, there are 4 bonds. So these guys try to get away. These guys try to get away from each other. And we end up with a molecular geometry, which is also known as tetrahedral. Has a bond angle of 109.5. It kind of spreads out on the bottom, almost pyramidal-ish shape, but makes like a triangle on each of the faces. That sort of happens in this case. So tetrahedral is both the electron pair geometry name and the molecular geometry name. Now, at this point, has either of those names been different? The electron pair name or the molecular name? It hasn't. And the reason for that is they are all bonding electrons. There's no dots on the central atom. So all these electrons are bonding electrons, which means they're attached to an atom, which means as those electron pairs move, so that those atoms, which gives you the same shape for both names because there's no non-bonding electrons involved, they're all the same type of bond. So whenever you have no dots on your central atom, both names will be the same. It is only when we start introducing non-bonding electrons to the central atom that we actually get a difference in the name, and the different name is going to be the molecular geometry name is going to start to differ. And that is because we are missing the atom and we have non-bonding electrons. So it gives the electrons a little bit more, because the molecule kind of moves a little bit more as a result of that. And we also get some different repulsion type forces that occur. So when we have dots and lines, bonding electrons, non-bonding electrons, there's different types of repulsion forces that occur. In what we were just talking about, sort of the bonding near bonding, which means basically lines near lines, that sort of repulsion is relatively acceptable. The next worst situation is where you got dots near lines. That then means that they want to get a little bit further away from each other. And they're able to do that again because those dots have no atom attached to it. So it's able to kind of flex out a little bit further away. The worst situation is when we get dots near dots. It's like they do not want to be near each other. Those non-bonding electron pairs will try to get as far away as possible. The result of that is because they're all still bonded, as electron pairs move away from each other, everything else kind of moves in accordance because they're all basically attached to each other. So the first sort of situation we come across that is your question, I think, which is SO2. So if we draw SO2 here, once again, looking at the central atom, the number of electron pairs is how many here? It is 3 electron pairs. 1, 2, double bond counts as only 1 electron pair. So 3 electron pairs. Number of bonds would be only 2. 1 bond here. Double bond counts as only 1. So that's a really important rule when you're doing geometry. Double bond, triple bond, single electron pair, and single bond. Something with 3 electron pairs. The electron geometry name does not change. So that is still trigonal planar. But now we don't have that sort of third bond here. So that allows these electrons to come down and this electrons to kind of go up. And as that one goes up, those guys kind of come down. And we end up with a molecular geometry of what is known as angular. I personally go with angular, but some people still use bent for this one. And some people use bent angular as well. So you might see a variety of names maybe. Some people use bent, some use bent angular. So a couple of different names. For us, we're going to go with just angular. So the bond angle here is less than 120 degrees. So this bond angle is less than the bond angle that you would see for trigonal planar, which is 120 degrees. Again, with the non-bonding electrons, they're able to kind of flex a little bit more. This has bonding near bonding electrons, non-bonding near bonding electrons. So again, these are things that make the molecules stretch out a little bit more. Next example here is a central atom where we have 4 electron pairs. Doesn't matter if they're lines, doesn't matter if they're dots around the central atom. So once again, 1, 2, 3, and 4 electron pairs. Number of bonds going to only be 3. 1 bond, 2 bonds, and 3 bonds. Something with 4 electron pairs, electron geometry is still going to be tetrahedral like it was before. Because we're missing that 4th bond here, the molecular geometry becomes something known as Trigonal Pyramid. And that's because kind of makes a pyramidal shape and like a triangle sort of shape there. So Trigonal Pyramid has a bond angle less than 109.5 degrees. So bond angle a little less than 109.5. It's like $1.07 in this case, something like that, in that ballpark. Let's take a moment to talk about 2 names that we just talked about here so far. And those 2 names are Trigonal Pyramid, which we have here, and Trigonal Planar, which is again 3 and 3 electron pairs, electron bonds. Those are different names, and on a test or something, you should not just write trigonal and let me choose, because I will choose wrong because I failed chemistry. So don't let me choose. You should not do the other thing too, trigonal Clearly that was plane and pyramid, one of those, right? So make sure you choose. Don't just write trigonal. They are different. They have different bond angles. They have different bonds. So you got to either specify trigonal pyramid or trigonal planar. Any questions on that there? Last geometry for you, because we don't do the expanded octet, which is good, is this one here. This again is something like water. It has number of electron pairs, 4. Again, 1, 2, 3, and 4. Number of bonds has only 2 bonds. Once again, something with 4 electron pairs. The electron geometry name is going to be tetrahedral. The molecular geometry is going to be something known as bent or V-shaped. And that's because in this case, we have all of the worst interactions happening. We have bonding electrons near bonding electrons, lines near lines. We have non-bonding near bonding, lines near dots. And we have dots near dots, which are non-bonding near non-bonding. So basically, these electrons decide we're going to go like this way, which makes these hydrogens drop down into this sort of bent or V-shaped type of geometry. Bond angle here, less than 109.5 degrees, about 104-ish or so, yeah. So that's why we're going to go with angular on the previous one, because the bond angle is actually different. It's less than a 120. Bond angle here is getting down into less than 109. So there is a difference. So for us, so it's not confusing. For the one that had the 3 electron pairs and 2 bonds, we're going to go with angular. Just to let you know, some people do call it bent and some people call it bent angular. So, but for us, we're going to go angular on that one to make it different than this one, which is actually always bent and V-shaped, bent or V-shaped. For this one where you have 4 and 2. Other questions? All right, so that's the best way to do geometry. I made like a table, I think it's on Canvas, of the geometry and kind of what to look at, but it's a good way to kind of do it. It's just electron pairs. This is like from your book as well. You got a similar table of all those things. All right, the last thing we're going to talk about in terms of geometry, and obviously you're responsible for the geometry, be able to draw Lewis structures, give both the electron pair geometry and molecular geometry names. Last thing we're going to talk about is molecular polarity. And molecular polarity talks about the molecule as a whole. Is the molecule polar or non-polar? If a molecule is polar, it will have what is referred to as a dipole moment. And we sometimes represent a dipole moment with that same arrow we use when we talk bond dipoles, where it points to the more negative side. This guy is the more positive side of the molecule. Polar molecules will have dipole moments. Non-polar molecules will not. So overall, in a polar molecule, there will be a positive side and a negative side. And overall, in a non-polar molecule, there will be basically no charge, kind of like a neutral. Electrons are being shared equally over the entire molecule. So let's take a look here. The simplest ones to figure out whether or not the molecule is polar or non-polar are diatomic molecules. So if you have something like H, or F, or O, it don't really matter. When we look at each of these things, the bond in each one of these, are these bonds polar or non-polar? Each of these bonds. Each of these bonds are going to be non-polar based on electronegativity, like 4 and 4, right? Equals 0 when you subtract it. So these are all non-polar bonds. Which means in this particular molecule, there is only one bond, and one bond. Which means if the one bond in the molecule is non-polar, and that's the only bond present, then the entire molecule is going to be non-polar as well. So because of that, this molecule will be a non-polar molecule. Now, if we take something like HF, the bond between H and F is a polar bond. And once again, that is the only bond there, which means that this would be a polar molecule, where we could draw our dipole moment like that arrow heading towards the fluorine in this side. So with diatomic molecules, because they really only possess one bond, if you know if that bond is polar or non-polar, that will also tell you the molecular polarity. The polarity of the entire molecule will be the same. Either it would be polar or non-polar. Any questions on diatomic? So those are pretty straightforward because there's one bond. If that bond is polar, then the whole thing is going to be a polar molecule. And if that one bond is non-polar, then the whole thing would be non-polar. Now, if everything was that easy, it would be great, but it is not, of course. So when we do get into molecules that have 3 or more atoms, you have to actually look at a couple of things. The 2 things you got to look at when you have 3 or more atoms, you have to look at, are there polar bonds? Try that again. Are there polar bonds? Obviously, if the answer is no, then it's going to be non-polar. And secondly, you need to look at the molecular geometry. Or the shape. Now, if we take something like carbon dioxide that we drew earlier, between carbon and oxygen, are there polar bonds between these two? Is the carbon-oxygen bond polar or non-polar? It is polar. Again, we don't need the electronegativity tables to help us. Carbon and oxygen, same row on the periodic table. They're from each other, which means oxygen is going to be more electronegative, which is going to create polar bonds. And if we drew our little dipole arrows, they would be pointing towards the oxygen here. The geometry here, the molecular geometry of this guy is 2 electron pairs and 2 bonds, which means the molecular geometry of this guy is what? Nothing with 2 electron pairs and 2 bonds, it would be linear. Yeah, so it would be a linear geometry. So what that means is we basically have a linear geometry. We basically have a straight line. And what's happening here is on one side, it is pulling the oxygen. On the other side, it is pulling the oxygen. I am actually pulling on my pen both ways. Is my pen going anywhere? It is not. So what happens in this case is, even though this has polar bonds, because of the geometry, it actually is going to be a non-polar molecule. And that is because these bond dipole arrows, these are also what are known in physics as vectors, I think. Yeah. They have direction, they have magnitude. Then I fell asleep. But I woke up long enough to remember that in certain cases, they cancel each other out, right? In other cases, they add to each other. Cases where they cancel each other out whenever they're going equal and opposite of each other. Kind of like pulling on a rope, like tug of war, right? Everybody pulls equally, nothing's going anywhere, so they cancel each other out. Also, if they're coming like right at each other and they're coming equally at each other, the door that swings, if you have people pushing right on the door on opposite sides, the door is never going to open, right? So they cancel each other out. So there are certain cases where you can have polar bonds like CO2, but because of the geometry of the molecule, it becomes a non-polar molecule because they do cancel each other out. Any questions on that there? Now, if we look at something like water, the bond between oxygen and hydrogen is also polar. So what happens is we do have polar bonds heading in this direction. The geometry here of this guy is bent, our V shape that we just did for electron pairs and 2 bonds. Now what we have is like a kind of like a V, and we got guys coming this way and guys coming this way, kind of like you're pulling from the top. So if you kind of pull it from the top, you might imagine the whole thing would start to move. And these guys actually add to each other, and this would be a polar molecule where we would have a dipole moment happening heading in this direction, where the oxygen side of water is more negative, the hydrogen side of water is more positive. In case you're curious how the vectors work like that, because this is going at this angle, you then would put the other guy at the tail of it, and then they add coming in this direction. Nobody wants to do that for sure, yes, but that's how that works, by the way. So this is going to be a polar molecule because of the geometry here. So nobody wants to draw vectors or think about vectors. So there's really sort of a quick, easy way that you probably always get the answer right in terms of molecular polarity. There are certain geometries which are symmetrical geometries. And what those guys for us, that would be trigonal planar and tetrahedral. And these are the molecular geometries. So if you have any of these geometries after you draw your Lewis structure and all the outside atoms are the same element, this guy will result in a nonpolar molecule. So for example, if you had something like this, between carbon and fluorine, it is polar, right? So we definitely have polar bonds happening here. Everybody on the outside is the same. They are all going to cancel each other out, and this would be a nonpolar molecule. Again, they're all basically equal and opposite of each other, kind of pulling equal and opposite of each other. A lot of people think about pulling on a string or a rope, and they all will sort of cancel out. Now, what would happen if I removed one of the fluorines and replaced it with a hydrogen? I now have some polar bonds still happening here. The carbon-hydrogen bond, polar or non-polar? It is non-polar, basically. So basically what you have in this case is like these three guys, not perfect geometry here, but you got these three guys kind of pulling towards the fluorine, and the guy on the back not doing much. He's actually, believe it or not, helping. He's actually going in that way too, a little bit. So you can kind of imagine the whole thing would sort of move, and then it would become a polar molecule in this case. So with these geometries, if you draw it, no dots on the central atom, everything on the outside is exactly the same. Pretty safe bet that the molecular geometry, molecular polarity will be non-polar. If you draw your Lewis structure, no dots on the central atom, everybody on the outside is not the same. It's a pretty safe bet it's going to be a polar molecule. So that's a very quick way that you could decide those two. Any questions on that there? There's also unsymmetrical geometries. And for us, that would then be angular. That would be Trigonal Pyramid. That would be bent or V-shaped. And basically what all these have in common are there are dots on the central atom when you draw your Lewis structure. And if all these guys, all the elements are the same on the outside, it will be a polar molecule in most cases. Like our water, basically, that we saw a second ago. Basically, all you have to do is go, I see dots, I see everybody on the outside is the same, I see polar molecule, basically. So what that basically leaves you for us is linear. So the only one you got to think about in the case of like CO2, they were going opposite of each other, which means it would be nonpolar. You could have all the dipole arrows heading towards each other, which would be nonpolar, but it is possible for a linear guy, obviously, that you could end up with, you know, maybe something all heading in the same direction, which then it would be a polar molecule. So linear is not too bad since it's a straight line. Again, if they cancel each other, then it's going to be nonpolar. But if they're all sort of heading in the same direction, it would then be polar. So if we look at some of the stuff that we drew, we can probably relatively quickly kind of go through them and figure out polarity or non-polar. If I missed the H there as well. Come here. Go. We did that one. We did this one. And we'll do like this one. All right. So looking at this one, should this be polar or non-polar? I see the central atom. I'm looking for dots. I see dots. Yes. I see everybody on the outside is the same. So dots and everybody on the outside is the same. That's going to be polar molecule. Yeah. How about this one? I see no dots, right? Everybody on the outside is the same. Should be a symmetrical geometry, should be non-polar. Yeah. Here I see no dots. Everybody on the outside is the same. Should be polar or non-polar. Should be non-polar. Yeah. Here I see dots. Everybody on the outside is the same. Polar or non-polar. Should be polar. So once again, if you draw your Lewis structure and there are no dots, it's the same, going to be non-polar. If you draw your Lewis structure and there's no dots, everybody on the outside is not the same, it's going to be polar. And if you draw your Lewis structure and there are dots on the central atom, it is going to be polar if everybody is the same on the outside there. So if I had this, polar or non-polar? It is going to be polar. I see no dots. Everybody on the outside is not the same. This will be polar. Yeah. Any questions on molecular polarity? So that's kind of the quick way you could do it based on your Lewis structure. Dots, no dots, and ours, everything on the outside the same, are different. Any questions on any of that there? Okay. That takes care of this chapter, I think. Any questions on that? Okay, hang on one sec here.